Okay, welcome everyone. Happy New Month. Welcome to this month's webinar of the AmNet Machine Learning Group. Today we have a scholar in our midst who is going to be presenting part of his work and what he has been working with. In fact, he was my student. I supervised his master's thesis, and he has been doing quite well. He's going to speak to us. He's going to present some important topics to us, very important topic today. So I want to hand over to Professor Dennis to introduce him. Professor Dennis, please introduce our speaker today.
Thank you, Prof. Welcome, all of you. I can see we have quite a number of people who have joined, and we are grateful to have you in our today training. My name is Dennis Mureithi from Chuka University, and I will be your host or moderator for this session. We are going to, sorry, I'm checking something here, to have a presentation on explainable AI for malaria prediction using Python. And our presenter today is none other than Peter Mwangi. Peter is a data scientist with a strong background in machine learning and statistical modeling. He owed a master's in data science from Africa Institute for Mathematical Science, Cameroon, and a Bachelor of Science in Statistics and Programming from Kenyatta University, Kenya. Peter specializes in developing applicable machine learning models with his thesis focusing on malaria prediction. His professional experience spans the health and banking sector, where he has worked on impactful projects such as OCR implementation, fraud detection, predictive analytics, and loan scoring. Currently, Peter is a data scientist and passionate about leveraging data-driven solutions to address public health challenges and enhance financial systems. He combined technical innovation with practical applications to drive meaningful changes in this critical industry. I now take this chance to welcome Peter Njoroge to take us through the presentation, and then from there we'll take questions later. Njoroge, you are welcome. Take over, kindly.
Okay, thank you for that introduction. So without wasting much time, we are going to start with the presentation. And once again, welcome to this webinar. Thank you for finding time to join. So we are focusing on explainable modeling, malaria modeling with improved accuracy. And when we say about explainable AI, this is when we talk about going beyond prediction. So let's say you are in, let's say a health professional has detected, maybe you have visited a hospital, and then after giving out your signs, let's say maybe you have a fever, you have a headache, you're vomiting, and there is a model now that runs. And after some time, the prediction comes out that you're suffering from malaria. So the model tells you that you're suffering from malaria, but you're not sure. You're not sure how the model came up with that decision. And that, therefore, is why the importance of introducing these explainable AI techniques to help us understand why the model said that you are suffering from malaria or you're not suffering from malaria. Which are those features that this model took into consideration? And therefore, this explainable artificial intelligence refers to machine learning models designed to provide human understandable explanations for their decisions and predictions, such that even a human being can be able to understand. We know that traditional machine learning models, this is especially the deep learning models, they are acting as black boxes. Black boxes, it means that we are not able to tell how they are making their, and therefore explainable AI comes in place to ensure that we are able to get the transparency or the understandability of how they are making the models. And therefore, the goal of this explainable AI in malaria prediction is number one, is to give us transparency. This is to make the decision-making process of the model interpretable. And number two is to have trustworthiness, to ensure that healthcare professionals and policymakers can rely on the model. So when the model gives them prediction that a patient is suffering from a particular disease, let's say malaria, we are able to trust because the model is able to give us an explanation of the features that it took into consideration. And of course, another goal is for regulatory compliance. This is meeting the requirements of AI-driven medical applications, which demand interoperability and accountability. So we are to do this model using Python. And
I kindly request those who have not muted to mute kindly, please. Keinde, and others, mute so that we can listen to our presenter today. Go ahead, Peter. Sorry for that.
So we are going to do this using Python. And as the rule says, and when you're doing any modeling, there's several steps that you have to take. So the first steps usually requires you to install all the required libraries or packages if you have not installed them. So these are several libraries that you need to ensure the end-to-end project. And for instance, you need libraries for data handling and visualization. You need libraries for machine learning models. You need libraries for explainable AI. So those are the three main libraries that you need. And for this work, we are going to see the 5 ensemble models. We are going to compare the 5 ensemble models, and we are going to pick the best models, and that model is what we are going to continue with on the explanation part. So this is the first part. So you have to install all these libraries. So you can install them by running that cell. So if you have not installed any of those libraries, you can do pip install any of the libraries, and you'll be able to install all those libraries. So after you have installed all your required libraries, now the second step will be to read the data file or to read the data set. For my case, we are dealing with the malaria data set. This is a data set that was obtained from Nigeria over a 4-week period study. And the link will be provided as well so that you can be able to check the data set. And you can click on that cell. So this is a simple Python code of reading a CSV file. And with that, your environment now is able to has access to that data set. Then another step for when you are modeling malaria is you need to understand the data set. You cannot just go to the modeling part without understanding how this data set is structured, how this data set looks like. So there's a very important step we call the exploratory data analysis EDA process. And the key steps here is to just check the data overview. We want to check the shape, we want to check the column names, we want to check the data types. We also check the missing values. If the data set has missing values, we check and we handle those missing values using the appropriate method. Also, we check the statistical summary. We check on the distribution of various columns. We also check the class distribution. This malaria modeling, we are focusing on class is a classification problem. Remember, there are generally two major types of prediction. We have this regression and we have classification. So for this problem is a binary classification. So it's either you have malaria or you do not have malaria. And therefore, it's very important for us to check the class distribution, to check if there is class imbalance. And if there is class imbalance, we handle it in the using appropriate methods. And also we can check on the correlation analysis. This is to check the relationship between features using plots like heat map. So using this cell, we are able to check the shape of the data set. So from that result, we are able to see that we have 337 records and 18 columns. And we can say df.head to check the first, just to check the first 5 rows. And from here, you are able to see your data set. You're able to see you have columns like age, sex, fever, cold, rigor, fatigue, and all these other columns. And your target variable is severe malaria. This is the target variable that you are going to predict. So it's either 0 or 1. 0 means the patient does not suffer from malaria, and 1 means the patient is suffering from malaria. So we can continue to explore the data set using the describe method. We are able to describe this data set. For instance, this age column, we are able to see the maximum age for this data set is 77, meaning that the maximum age of a patient, 77 years. The minimum age is 3 years, and the mean age is 30 years. So you're able to get descriptive analysis. And there we can check on the data type using that command. So we are able to see all the columns, they have integer as data type. And we continue to explore the data set just to see the columns alone and run that cell. We are able to see the column names. And the next step is to check on the missing values. Can run that command. And when we run this command, we find that our data set does not contain any missing values. So we are not worried about the missing values because our data set is clean. So we continue. So we want to see now the correlation. Want to see how different features correlate with the target variable. Target variable, I've said, is the severe malaria. So when you run this cell, you are able to see this correlation matrix here. So if you can take a closer look at this matrix, you are able to see, for instance, age has a correlation of 0.06. Sex has a correlation of 0.01, 0.00, actually no correlation. Fever, 0.01, cold, 0.07. So generally, the features are not much correlated with the target variable. If you see this scale, if it's color blue, it means that the correlation is not as strong. But if you happen to see a feature that is going towards red, it means that feature is highly correlated with the target variable. So for this data set, the features are not really correlated, but of interest is that you can see some features like age, like sex. Sex has 0.00, meaning that this sex does not have any correlation with the target variable. And therefore, when we are modeling, we can drop some features. Those features that are not correlated, we can drop them because they do not impact the prediction. And therefore, we can set threshold. We can also visualize this correlation better using heat map. Heat map now gives us a general picture between different features. So the dominant color there is blue, meaning that most features are not really correlated with each other. And then with the help of the heat map, we are able now to set a threshold. Let's say we want to select features with correlation coefficient above a threshold of 0.01. And therefore, we are able to eliminate some of the features. For instance, you'll notice that feature like sex will be eliminated. And That is also part of EDA. And now, also another part of EDA is to understand the distribution of our target variable. Remember, we are predicting whether a patient has malaria or a patient does not have malaria. So using a pie chart, we are able to see the distribution of the target variable. So we are able to see the data set, the 65% of cases, they do not have malaria. And 34% of the cases are suffering from malaria. So from this, we are able to see there's a class imbalance. There's a class imbalance. And if you continue modeling with this class imbalance, your model might not perform well. So you need to address this challenge by balancing these two classes to at least to a level percent, let's say 50%. But for now, our data set is imbalanced. Okay, so we can visualize it better using a bar chart. So we are able to see 221 cases do not have malaria, while 116, they have malaria. Okay, we can continue. Remember, EDA is when you understand your data set better. So you can take some time there to just try to understand the distribution of your data. So here we can check the distribution of different columns. So here, what we can see is that, like for instance, age, is a normal distribution. And most of these other features are binaries. It's either 0 or 1. From these plots, we can clearly see that. So after that, now we have already understood our data set. We have seen that the data set does not have missing values. We have also seen class imbalance. We have also seen the distribution. Now we can go to modeling. And here we now begin by splitting our data set into training and testing. So remember, our model we run on the training data, and then we are going to use the portion that we left for the testing purposes. So we are going to divide 70% of the data set will be used for the training, and 30% will be used for the testing. So by the help of this code, we are able to split. So you split the target variable from the rest of the columns. So the X will be the independent and the Y will be the dependent variable. Can run that. And then we are going to split now the data set into training and testing. So from here, we are able now to see the training set has 235 records, while the testing will have 102. Then the models used here, we are going to test on 5 different models. These are called ensemble models. These are models that combine with other models to create stronger models. So we are going to focus on random forest, adaptive boosting, AdaBoost, gradient boost, XGBoost, cat boost. So we are going to see the performance of these models. And then we need to scale our data set, because when you scale, you now ensure that the model fits better. When you standardize, you ensure that everything comes in between 0 and 1. So if you had an outlier, so when you do when you standardize the data set, it's able to bring in to a scale of 0 to 1. So it's an important step to do. And then now, from here, we are able now, we can store our models, our 5 models in a list using this command. So we are just going to be calling out on these store models variable. It's like a variable. And then now from there, we do something called hyperparameter. Remember, different models, they have hyperparameters. These are parameters that help this model to best bring out an prediction. So you are able now to define different parameters. For instance, like random forest, N estimators, you can define 100, 200, 300. and maximum depth 10, 20, 30, and you're defining in a list. So when we are going to run this code using now what we call the grind search. Grind search will help us get the best parameters for each model. So these parameters are very important. And running this one, also I'm going to do the 10 folds using this grind search CV. This 10 folds is like 10 subsets. So I'm training on 10 subsets just to get the best prediction out of this. So this code is going to take some time. So I'm not going to run it now, but after running, you're able to see the following output. You're able now to get the best parameters for each model. For instance, let's say random forest, you're able now to find your best parameters for that particular. Therefore, these are the parameters that you're going to use in modeling. The next step is the next step now is to train our model. We have already stored our models in a list. We have already gotten the best parameters for each model. So we are just going to loop over each model now to train over the training data set and to get now our results. And when we get the results, we are going now to test on different metrics like accuracy score. We are going also to see the MCC, Murphy correlation coefficient. We are going to see balanced accuracy, Cohen-Kappa, precision recall, F1 score, and other metrics as well. So with the help of this code, we are able to come up with this table here. So remember this is when we have not done any data balancing. Remember the target variable was imbalanced. So first of all, you can run the model using the imbalanced data set to see how the model works or to see the performance of those models. Then after this stage, you can do the balancing now to see if the model will improve on the accuracy. So before modeling or before anything, we have run this and you can see that the accuracy are quite low. But you can see that, for instance, AdaBoost is having an accuracy of 0.63, and we can see these other metrics that will measure our model performance. They are quite low, like this MCC is 0.00, balance accuracy is 0.5. These other ones are 0.00. If you also look at other model like gradient boost, Cohen-Kappa is 0.1, and generally the models did not perform well on this imbalanced dataset. So we continue to evaluate. There's something called confusion matrix. Confusion matrix will help you to gauge how well the model classified the classes. Remember, there are two classes, positive and negative. So you're able to see, to tell how well this model classified these classes. For instance, we can be able to see the case of random forest here. The case of random forest here, we are able to see that the model has classified 56 cases as cases with no malaria and 7 cases with the malaria, and it has misclassified some of the classes from these 2 cells. And you can also evaluate using ROC curve. This is a curve that will help us to tell how well this model are working. So this class normally ranges from 0 to 1 with a scale closer to 1, meaning that is a good model, or the model is able to distinguish between those 2 classes. So when the probability tends towards 1, it tells you that the model is performing well. So as you can see here, the scores are quite low. They have an average of 0.50. So this means that this imbalanced data set was not really able to distinguish these classes, and therefore the model accuracy is not guaranteed here. So after that, now we can do balancing of the classes. So there are different methods of balancing. You can test using different methods just to check which method will work best with you. There is undersampling, there is oversampling, there is SMOT. So for this case, you're going to do oversampling. So oversampling is when now you raise the minority classes to come to the level of the majority classes. And I had mentioned before, 64% was non-severe malaria, while around 30-something% was malaria. So that was imbalanced. So after balancing, we are able to see now this bar graph. We are able to see the bar graph now is on the same level. So meaning that now we can comfortably do the modeling again now using this balanced data set. And after balancing, we again can store our models again as a variable or use the variable that we had stored earlier, depending on your preference. We again use the fastness parameter we found, and we loop over these models to run this table. So after running this table, we are able to see the following results. So we are able now to see the models have improved on their accuracy. For instance, if random forest was around 0.54, this accuracy score can be able to see now the random forest has improved up to 0.76. The also MCC, we can be able to see it has improved. Also the balanced accuracy, precision, look at precision, which is a very good metrics that helps us to tell that the model is really able to distinguish between the positive classification, 0.8. And also cut boost here, you're able to see cut boost performing well at 0.74. And also other metrics as well, they are quite high, 0.82. So with taking in mind that the data set was quite small, we had only 337 records, but we are able now to see that our model has improved after balancing the classes. And therefore now from this table, we can pick on best performing models. This is, we can pick on random forest, and we can also pick on cat boost. These two models, they seem to be performing well on this malaria dataset. And after this, we can run on confusion matrix just to see, and we can be able to see different confusion matrix for each of the models. We are able to see how the positive classes were classified, the negative classes were classified, and the misclassification that were done on those confusion matrix. And again, the ROC curve that helps us to gauge or to check the performance of these models, we can run. And from this table here, we are able to see that ROC curve is on a scale of 0 to 1. If the data point is, or if the prediction or the probability is tending towards 1, tells you that the model is performing well. So from here, we are able to see that cat boost has a 0.83, so meaning that this is a good model for our case here. And also random forest at 0.82 is also performing well. So we can proceed on with the two models for our explainability. Remember that the end goal, not just to stop at prediction, but rather to go beyond prediction and to see how these models are making the decision. And from now there, we have identified random forest and cat boost as best performing models. So we can try to see feature importance, top 10 features that random forest took into consideration. from this bar graph here, you're able to see now age as the top performing feature. This is the age that this random forest classifier really took into consideration. So it gives the model more weight. So age followed by headache, cold, and so on. And we can also do the same for a cat boost classifier. So just need to call this function cat boost classifier, and you get the top 10 features again. According to cat boost again, we have seen age emerging the top feature again for cat boost classifier. Also headache is among the top 3 features for both models. So with that now, we come to now explainability. Explainability now is when now, of course, now we have seen the model is able to tell us if you're suffering from malaria or you are not suffering from malaria. So we want to understand why did the model make that decision. We want now to understand why the model made those decisions. Which are these features that the model took into consideration? So there are several methods of explainability. We are going to focus on 3 methods. The first one is LIME. This is local interpretable method. That we are also going to focus on SHARP, and we are also going to see another method called permutation feature importance. So if we can just briefly describe LIME, LIME will give us an explanation of an individual instance. So let's say a data set contains 100 records, but you are only interested in the record from that 100 records. So LIME gives you a local interpretability, and therefore you are able to now focus on individual cases. So you need to install the LIME library, and you need to use these the explainer. You need to now use the LIME explainer here. So if you see this line here, if you can see this line that I've highlighted here, we are going now to test on the X test. X test is our test data set. And iLog, I've defined iLog as 0, meaning that I want the first record. I want to understand the first record that I have. Maybe a patient has come and he or she has given out he has said maybe he's suffering from fever, he has a headache, he has Coca-Cola urine and other signs. So we wanted to see how this model is performing. So when we run this LIME, we are now able to see the prediction. We are able now to see the prediction. For instance, here we are able to see that this patient, 0.55% patient is suffering from malaria, and 0.45% the patient is not suffering from malaria. So the prediction is not quite clear because it's like a half-half probability, but nevertheless, we are able now to get an explanation. Why did this random forest LIME explanation tell us that 0.55% of this patient is suffering from malaria? And on your left, or rather on your right, you are able now to see this explanation here. And you're able to see that the feature that the model took into consideration was headache, age, hyperexia, Coca-Cola urine, and diarrhea. So meaning that you are able now to get an explanation of how this decision was arrived at. For instance, here, if you can be able to see this line here, you are able now to see that headache has been given a 0.16 probability, meaning that that probability is tending towards predicting that this patient has malaria, and also age is greater than 41. So you're able now to get individual explanations. Because the age of this particular case was 57. And therefore, this model is actually saying that the age is greater than 41. So it's actually pushing towards this prediction. Let's take another instance. Can take this iLog, we can set it to 1 just to see another instance. When we run this instance here, we are able now to see that 95% of this case is that this patient is suffering from malaria. So, and why did the model say that 95% is suffering from malaria? You come on your table here and you see these features that are color. The color is orange. You can see the 95% is orange, 0.05% is color blue. And on the other end, you are able to see the corresponding colors and the corresponding features. So for instance, this 95% is about headache, hyporexia, rigor, cold, convulsion, diarrhea, anemia. So those features are the ones that contributed towards this 95% prediction. And actually, you can be able also to see the individual probabilities on this line here. You're able to see the different probabilities. And that is for random forest. You can also do the same for cat boost. Again, the same thing. If we run an instance, you're able now to see the prediction. For example, this instance, 0.79% of this instance is that this patient is suffering from malaria. And you are able to see the orange features that are contributing towards this prediction. And we can now go to another explanation, explainable AI technique called permutation feature importance. This permutation feature importance will generally tell us which features are contributing towards prediction. So we can start with cat boost, permutation feature importance, and we are able to see when we run this code, it's able to give us some probabilities. So for instance, when you check this bar graph here, we are able to see that age is the most important feature that the model is taking into consideration, followed by headache, convulsion, cold, fever, bitter tongue, and so on. But if you see at the end here, there is a feature called vomiting. The model is not really taking into. And then you can go to random forest. Again, for random forest, the same case, we are able to see age is the most important feature, followed by headache, cold, bitter tongue, and so on. But at the end, you can see vomiting again, although it's not color red, but is the least important feature. And we go to the final explainable technique called SHARP. So SHARP will give us general contributions of features and will try to show us that which features are tending towards this prediction. So for instance, this is the SHARP plot. The SHARP plot looks like this, and you can see a line on the middle there running across. So you are able to, on one side, we have negative instances. On the other side, we have positive instances. So for instance, here, our SHARP tells us which, look at the data point, the spread of the data points. There are so many and they are clustered. And if you can see the line dividing across the two, you can see the clustering is more concentrated towards the positive side for all the features. In fact, for all the features, you can see this line that is running across. You can see most features are on the positive side, meaning that these features are pushing towards predicting malaria or not predicting malaria. So, but again, we get a ranking from the most important feature that this SHARP is taking into consideration. For instance, age. Age has been ranked high, and you can see the clustering is also spreading across. Then number 2, we can see headache, and we can see even the scale here tells us is from blue to red. And if you see red, it means the high concentration. And therefore, with now this SHARP, we are able now to understand the most important feature of our model and the features that are really pushing towards prediction. And you can do the mean absolute SHARP. This is another plot of SHARP just to get a good overview. Again, age, headache, and so on are being ranked. So I've come to the end of this presentation. So in a nutshell or in summary, we have done modeling, malaria modeling using Python. So the first step is to get your data set. Then the second step is to load all the required libraries. Then you need to understand your data set. You need to do exploratory data analysis. And after that, you have to do now modeling. You can do modeling before balancing the classes, and then you can do modeling after balancing the classes. Then when you get your best performing models, now you can be able to go further now to explanation, now to get an explanation on how the model are arriving at decisions. Using now we have checked on 3 methods, that is LIME, SHARP, and permutation feature importance. So by leveraging these techniques, now the healthcare professionals are able now to trust these models, are able now to get a clear understanding on how these predictions are made. And I've come to the end of the presentation. I take it back to the moderator.
Thank you, Peter, for a nice presentation. And we are happy that we have been able to learn quite a number of things on how to undertake modeling in Python. I want to request participants, if you have an area that you require clarification, you have a question, this is the time to ask the questions. We will take 3 questions, a bunch of 3, and then the presenter will be able to respond to them. Professor is also there and will also assist in responding to these questions. So feel free to ask questions. If there is any question on the chats, I will inform the presenter. So feel free to ask your question.